that today presenting along with me will be Andrew, Rania, and Geth. Today we will be going over the following: our project justification, our research question, methodology, current findings, timeline, and finally team dynamics and challenges. Here you'll see a photo taken from the perspective of someone with normal vision. This next photo is taken from the perspective of someone with age-related macular degeneration, or AMD. As you can see, for someone with AMD, the center of their vision is blurred and darkened. AMD is one of the leading causes of vision loss for people over the age of 50. Currently, over 11 million people in the United States suffer from some form of AMD. AMD affects the macula, a highly sensitive region in the back of the eye. The macula has a high density of cone cells, which are responsible for vision acuity. AMD is characterized by high levels of oxidative stress in the retinal pigment epithelial, or RPE cells. There are two forms of AMD, dry and wet. The more common form, dry AMD, is characterized by the presence of drusen in the macula. If left untreated, this will progress to the more serious form, wet AMD. Wet AMD is characterized by the abnormal growth of blood vessels in the macula. We will be focusing our attention on dry AMD because there are no current treatments for it, and because it progresses to the more severe and irreversible wet form. Because AMD is characterized by high levels of oxidative stress, we wanted a drug that reduces oxidation. Therefore, we are using curcumin, the active ingredient found in the Indian spice turmeric. Curcumin is used around the world for its antioxidant and anti-inflammatory properties. However, because it's hydrophobic, it has a low bioavailability in the body. Therefore, in order for us to use curcumin to reduce oxidation, we need to increase its bioavailability. Which brings us to liposomes, which are lipid nanoparticles. Liposomes have both hydrophobic and hydrophilic properties. This allows us to store our hydrophobic curcumin in the hydrophobic lipid bilayer. It is also more bioavailable in the body because of its hydrophilic exterior. It's also beneficial for our task because of its self-assembly properties and because we can easily control its size. Currently, all treatments for AMD are extremely invasive and involve a series of injections to the eye. These injections are costly and uncomfortable for patients and might also deter them from getting treatments for their disease before it progresses too far. Therefore, we are trying to use a topical application to deliver our drug. We'll also be testing the addition of molecules and surfactants to increase topical absorption. We found that research shows that a successful delivery of liposomes to the back of the eye is possible. For example, the drug Avastin, one of the major treatments for AMD, has been delivered liposomally via a topical application. Which brings us to our research question. How can curcumin be encapsulated in a liposomal nanoparticle complex that can be delivered topically to prevent the progression of age-related macular degeneration? Next, Andrew will be presenting the methodology section of our project.
Thank you. So, we decided to approach our research question with a three-phase methodology. Phase 1 is creating the liposomal complex. Phase 2 is testing the complex, specifically in vitro cell culture studies. And phase 3 is ex vivo modeling using animal eyes. We decided to divide our project into 3 phases so that we can focus and specialize our talents of each individual members. However, as we are addressing one single question, it is essential that each member stays accountable and up to date for the progress of each phase, because each one is related and influences on the progress of the other. Phase 1 is creating the liposomal complex. It is a standard procedure which I'll walk you through in brief here. First, we mix our drug, curcumin, along with lipids and cholesterols, which are similar to those in animal membrane cells, to allow us, easy interface between the liposomes and the cells which we're going to test. They're mixed in an organic solvent. We use chloroform, which is essential for both dissolving these different types of compounds, as well as its ease of evaporation. We are able to evaporate chloroform relatively easy and quickly, which leaves us with a dry lipid film. This dry lipid film we can then hydrate using an aqueous solution of our choice. The aqueous solution we choose is sucrose, biologically neutral and safe solution to store our liposomes. We can choose, however, a number of hydration solutions, which is one of the powers of this technique. Through hydration and stirring, we are left with multiple liposomes, as you saw in the previous slide, bilayers with a curcumin hopefully stored within the bilayer. Through a process called extrusion, you're able to downsize these liposomes into uniform and specific desired sizes. And finally, through some purification techniques to remove excess curcumin that has not been stored, we are left with essentially the final liposome, which we can analyze through spectroscopy and microscopy to determine the accuracy of our liposomes. Currently, we have successfully created a curcumin encapsulated in liposomes. We are currently working on increasing the efficiency, as well as adding surfactants, which are essential for the topical delivery of these liposomes. Phase 2 is testing the RPE cells. So what we are going to do is use cell cultures as a sort of controlled situation in which we test the efficiency of our treatment on the sort of AMD-induced cells. We use ARP19, a cell line that's cultivated from human cell or RPE cells. The basic methodology is as follows. We grow them up, we treat them with liposome curcumin, and then we damage them afterwards with hydrogen peroxide. This is to simulate the effect of a preventative treatment of our product rather than treatment afterwards. We're then able to use standard assays to quantify the amount of oxidative damages within the cells on DNA and proteins, as well as how cytotoxic our product is to the cells. Included, of course, we also have various controls to control for unwanted effects of perhaps the free curcumin or the unloaded liposomes, as well as a no treatment control and a DMSO control, which will kill the cells and show us a base level of cytotoxicity. Currently, we have done most of the controls. A lot of work has gone into determining good levels and concentrations to use of each one of these ingredients. Phase 3 is modeling. So what we decided to do, because of time restrictions, we are using ex vivo eye models, as in tissue and eyes directly harvested from animals used in other labs. Our methodology currently is rather simple. We soak the animal eye tissue in an antilisome solution. Then, after a certain amount of hours, we can fix the tissue, we can dissect it into its various layers. Of course, we'll be focusing on the back of the eye, which includes, if you can see it or not, the sclera, the choroid, and the retina. By dissecting the eye into these 3 layers, we're able to view, using fluorescent microscopy, the amount of curcumin that has permeated through each layer. Now Shivami will talk about our current findings and results.
Thank you. So in terms of our current progress, we've successfully been able to synthesize and quantify curcumin encapsulated in lipid nanoparticles. We've also begun initial experimental setup for our in vitro and our ex vivo systems. So in the image you see here, we've been able to successfully encapsulate curcumin inside our liposomes. So the circles that you see in the picture over here actually show curcumin being encapsulated in the liposomes. And in order to verify whether curcumin is actually inside them, in the bilayer, we're able to use fluorescence microscopy. So the green fluorescence that you see on here shows the curcumin is actually inside the liposomes, which leads to the next question of how much curcumin is actually in them. In order to do this, we have to generate a standard curve from which we can back calculate the amount of curcumin that is inside the liposomes. So as of now, we were successfully able to generate an initial standard curve relating the amount of curcumin that we have in solution, our hydration solution, specifically sucrose. And from this, we can back calculate exactly how much curcumin is actually encapsulated in the liposomes. And based on this efficiency, refine our initial process for making the curcumin encapsulated liposomes. Our next part of our project was to be able to design our in vitro system. So as we see here, curcumin is cytotoxic in very high doses. After 75 micromolar, pretty much the cells are dead. There's 20% viability. And so as a result, we decided to stick to a concentration somewhere lower than 25 micromolar, as this is where the cells are mostly viable, and it also serves as an upper limit for all of our other testing for phase 1, as it gives us a good idea of exactly how much curcumin is our maximum amount that we can load in before we actually start to harm the cells instead of help them and protect them. So over here is a visual representation of the data shown on the previous slide. So As we see here, in the undamaged cells, the 0 micromolar curcumin, we see that the cells have really grown, they've proliferated, taken up the entire visual field. But in the 25 micromolar solution, the cells are starting to come off, they're starting to die, indicating that after this point, the cells are starting to die, and we've reached our upper limit of curcumin in solution, and for our in vitro testing. So, as mentioned before, in order to be able to simulate the effects that AMT has on RBE cells, we decided to use hydrogen peroxide. So from this figure, we see here that at about 500 to 7, or 0.5 to 0.7 millimolar, our RBE cells start to die off, and that's where we really start to see this oxidative damage starting to take place. And as a result, we decided to stick to something in that range in order to simulate the effects that AMT has on RBE cells. Phase 3 is currently working on practicing and perfecting dissection techniques, as dissecting and isolating the individual layers of the eye and being able to qualitatively analyze them is an intensive process and involves a lot of precision and technique. So we've currently been able to secure a stable source of eyes to practice these dissection techniques and be able to consult with many experts in the field. And now INJECT will talk about future challenges and our team's dynamic.
Thank you, Saramia. So for the last part of the presentation, I'll be going over our gemstone timeline, our recent and future challenges, and also our advice for freshmen. So looking at our timeline, this semester we're continuing all phases of our research, and next semester will be dedicated to finishing up the tests and assays that we're doing, and also collecting more data for our project. We'll then compile all our findings to present at undergraduate research day. Next fall, we'll be wrapping up any experimentations that we still have going on, and also beginning data compilation and data analysis. We'll then compile all of our results and submit our final thesis and present in senior thesis conference in spring of 2017. So far in our research process, we have run into two main challenges. The first is just trying to find a constant source of animal eyes for ex vivo testing for phase 3. And the second is just trying to finalize our methodology and figure out which tests and assays were the most appropriate to use in order to test our research question and whether they were feasible given our timeline. We anticipate some more challenges in the future. The first is just trying to stay organized and be able to coordinate between all phases of our research over a long break, since all of us have different plans over the holidays and also busy schedules during the year. The second is just trying to figure out a best way to analyze our data and how to best interpret the results that we get from our experimentations. So we have experienced quite a lot as a team since Team Formation Day, so we want to share with the freshmen some advice from what we have learned. So the first is to focus on team dynamics. You will be working with your team for 3 years, so it will make the process a lot more efficient, a lot more enjoyable if everyone was able to communicate and get along well with one another. So one of our big team traditions is having a team dinner each semester, which I think everyone really enjoys, not only because of the food, but because we have time to bond and get to know one another outside of gemstone and research. The second piece of advice is just to be open to changes in your project. It will change your initial project proposal, so just be receptive of new ideas. If you have any problems or conflicts with the team, make sure to talk it out openly. It's important for you to be able to work out the problem and communicate through as a team in order to find a solution. And the last piece of advice we want to share with you is just to have a positive attitude and open mind and have fun with your research. Even if things don't go smoothly, you'll still have learned so much from your experience at gemstone. And if things do go well, then you'll have great research to show for it. So we would like to thank our mentor, Dr. Halima Randa Espinoza, the gemstone staff, Dr. Justin Kerr, our librarian Eileen Harrington, and our method specialist, Ian Gould. We would also like to give a huge shout out to all of our amazing contributors for their support in our project. Thank you, and we would like for you guys to ask questions.